Hello everyone, before we get started, I'd like to bring some things to your attention. First, I'll be publishing all of the work associated with this video to my GitHub, the link to which you can find in the description. I've also done this for all of my previous videos if you're interested. Second, I'd like to point out that this video will be in more of a presentation style than my previous videos. This presentation is a modification of a talk I gave on the work I did for my undergraduate thesis, and I'm happy to share it with you all today. The topic of conversation will be one of my favorite combinatorial objects, the polyomino. But what is a polyomino? A polyomino of area n is a shape in the plane constructed by joining n unit squares called cells along their edges. During this presentation, we will refer to polyominoes of area n as n-ominoes. Polyominoes can also be seen as a generalization of the domino, where instead of just attaching two squares together, we attach 3, 4, 5, or so on. On this slide, we can see a domino, or a 2-omino, as well as a 6-omino, a 10-omino, and another 10-omino. But what isn't a polyomino? We see that this cell isn't connected edgewise to this set of cells, which are connected edgewise, and similarly, this set of cells isn't connected to this set of cells edgewise, and so both of these wouldn't be considered polyominoes. Notice, however, that our definition for polyominoes does allow for holes. So here we see a 7-omino with one hole, and here we see a 14-omino with two holes. As you might have noticed, there are very famous examples of polyominoes in the Tetris pieces. In fact, the Tetris pieces, and their rotations and reflections, consist of all 19 4-ominoes. So all possible shapes you can make by concatenating 4 cells on their edges together. One might ask, naturally, then, for a given number of squares, how many shapes can you make? Let's let Tn denote the number of n-ominoes. The first couple terms of this sequence are 1, 2, 6, 19, 63, and so on. For n is 1, it's pretty clear to see that you can only make one polyomino with one unit square. Similarly, for 2, we can either make a horizontally oriented domino or a vertically oriented domino. With a little bit more work, you can verify that given 3 unit squares, you can make 6 total polyominoes. And we already saw that the Tetris pieces, again with their rotations and reflections, in total amount to 19 different shapes. This is a pretty famous sequence, and if you're interested in further study, it's helpful to know that T sub n has index A001168 on the OEIS. This sequence has been enumerated up to n equals 56, which is a pretty massive number, and as you can see, the polyominoes get pretty complicated and strange looking with this many squares. The total number of polyominoes you can make with 56 squares is this massive number, which has 32 digits. However, it's unknown at n equals 57 and beyond how many polyominoes there are exactly. That's because these polyominoes actually are very difficult to count as the number of squares gets larger and larger, and even computing this T56 requires incredibly efficient algorithms running on a supercomputer to get the exact result. It is widely believed that there does not exist a general formula for returning the exact value of T sub n for a given n in which we could compute these values other than using computer algorithms. So we're kind of at an impasse here. We're really interested in these shapes, but we can't enumerate them past n is 56. So what do? If we still are interested in studying these objects, we instead start studying what are called polyomino families. But what are those? Polyomino families are restrictions on the form polyominoes can take as to introduce some type of additional structure. The rest of this presentation will study a polyomino family that I studied as part of my undergraduate thesis, the minimal inscribed polyominoes. To construct a minimal inscribed polyomino, start by picking an n by m grid. A polyomino is minimal inscribed when it touches all 4 sides of the grid and is of minimal area, that being of area n plus m minus 1. For that minimal area condition, another way to think about it is if we remove a cell from a minimal inscribed polyomino, it either fails to touch all four sides or fails to be a polyomino, or both. On the left here, we can see an example of a minimal inscribed polyomino in a 7x5 grid. And on the right, we can see an inscribed but not minimal polyomino in the same grid. It's important to verify why that example is not considered minimal. Just to hammer the point, let's do some practice together. Which of these pictures in the 5x5 grid are minimal inscribed polyominoes? Pause now to check for yourself. Okay, now that you're back, hopefully you verified that the top left is not minimally inscribed because it doesn't touch all four sides. The polyomino on the top right and bottom left are considered minimal inscribed, and the cells on the bottom right are not minimal inscribed because they do not form a polyomino. One might ask, now that we've seen a couple of minimal inscribed polyominoes in the 5x5 grid, how many are there? Well, let's enumerate them together. As this animation runs, we'll get to see all of the examples that verify this condition. And there we go. It turns out there are 497 minimal inscribed polyominoes in the 5x5 grid. What about a general n by m grid? Goupil, Cloutier, and Newbound in 2010 showed that the number of minimal inscribed polyominoes in an n by m grid for n and m greater than 1 is this expression here. We won't go through a full proof of this result here, but I'm going to show one of the main ideas of the proof so that we can understand at least where one would start enumerating these objects. First, let's let S be the set of minimal inscribed polyominoes in a given grid. Then S can be decomposed into three sets, that being the set of polyominoes that touch 0 corners, called S0, S1, which would be the set that touches 1 corner, and S2, which would be the set of polyominoes that touches 2 or 3 corners. And on this slide we can see examples of members of each set. So we see in S2, on the leftmost polyomino, we see that it touches 2 corners. Then in the middle, we see a polyomino that touches 1 corner. And then finally the polyomino on the right, which touches 0 corners. And these are all in the 4x4 grid. It turns out that enumerating S2 is the basis for enumerating S1 and S0. And so we will just focus on enumerating S2. So S2 is the set of polyominoes that touch 2 or 3 corners. So how many polyominoes are there in a 5x4 grid that belong to S2? It turns out that the question of how many minimal inscribed polyominoes there are that touch those 2 corners is the same as how many paths are there starting from the bottom left cell and going to the top right. Here is an example path now. This path is formed by the command sequence, if you will, of up, right, right, up, right, right. A path is actually uniquely identified by this set of instructions. And so the question of how many paths there are is the same question as how many ways can we rearrange 3 U's and 4 R's into a unique sequence. And for those familiar with an introductory course in discrete math, you'll recognize this as an example of using the choose function. And in fact, we'll see that the number of paths is the width minus 1 plus the height minus 1. Choose the width minus 1 to get, in general, the number of paths between these 2 corners. So in our example, we have 5 minus 1 plus 4 minus 1, choose 5 minus 1, which is 7 choose 4, which turns out to be 35 unique paths that include those 2 corners. This is a general idea for how one arrives at that previous result. There's more to consider, and there's actually a couple polyominoes in S2 that we haven't enumerated, but this is the core idea of the proof. My hope for my undergraduate thesis was to find other examples of nice results like what we saw, this time with other grids and with other shapes. So what we're going to do is we're going to generalize the enumeration of minimal inscribed polyominoes to minimal inscribed polyforms. So a polyform is very similar to a polyomino. Instead, we use a general unit polygon. So we could use unit triangles or unit hexagons, and here we can see an example of a polyform formed with unit triangles. Polyominoes can then be thought of as polyforms made up of squares. So the question I asked for my thesis was pretty simple. What can be said about other grids in the plane? Here we can see a triangle in the triangular plane, and then we can see a minimal inscribed polyform in that triangle. One last thing to add is we need a sense of scale for the triangle, like how we had a width and a height for the rectangular grid. So what we'll do is we'll let n designate the number of triangles touching a side. And the above case we can see is n equals 5, because we see that 5 triangles touch the bottom side here. So here are some examples of polyforms in different sized triangles. So we see an example in the n is 3 triangle and the n is 4 triangle. And if we were to enumerate all polyforms in these smaller triangles, we get a sequence. So if we start at the n is 1 triangle, we have 1 minimal inscribed polyform, and then the n is 2, we have 3, n is 3, we have 12, n is 4, we have 44, and so on. I showed in my thesis that the number of minimal inscribed polyforms in a triangle of size n in the triangular grid is this expression. So it's similarly nice to Goupil, Cloutier, and Neubaum's result for polyominoes. But we can keep going. We can study more triangles. So here we have a triangle in the hexagonal grid, as well as a minimal inscribed polyform. Again, let's let n designate the number of hexagons touching a side. The above case, again, is n equals 5. Here we can see some more examples for n is 3 and n is 4. And again, we can take a look at the sequence as the numbers get larger. So in this case, the sequence goes 1, 3, 10, 32, and so on. I showed in my thesis that the number of minimal inscribed polyforms in a triangle of size n in the hexagonal grid is this expression. The third and final triangle I worked on was the triangle in the hexagonal triangular grid. In the same vein, I show both the grid and a minimal inscribed polyform, but I'd like to point out that in this grid, we consider just the triangles as touching a side, not the hexagons. You can see some more examples here in the n equals 3 triangle and n equals 4 triangle. And again, the sequence starting at n equals 1 goes 3, 21, 125, 693, and so on. And in general, I showed that the number of minimal inscribed polyforms in this grid is this expression. I really like this formula in particular because, similar to how Binet's formula needs to invoke irrational numbers to answer a question about the integers, this formula uses rational numbers to answer a question about the integers. So I really like this formula, and it was one of my favorite results I found while working on the thesis. After this, we're going to get into a much more involved enumeration question. That grid was the Aztec diamond. So the Aztec diamond is a very famous shape in combinatorics. If you're familiar with Mathologer's Arctic Circle video, a very great video that gives a very deep treatment into a question about Aztec diamonds, you'll be familiar with this shape. Here we can see a 2x2 and a 3x3 Aztec diamond. Again, now we'll be talking about polyominoes again because we're dealing with squares. Just like with anything else, we need to define what's considered a side. And so what we'll do here is I'll provide these nice colorful little diagrams where each distinct color is its own side. So This is pretty analogous to what we saw with polyominoes. It's kind of like a rotated rectangle in the square grid. So red is a side, blue is a side, yellow is a side, pink is a side. And this is also helpful to see why we refer to these Aztec diamonds as 2x2 and 3x3. As we can see, there's 2 squares on the bottom side and 2 squares on the right side. And similarly, there are 3 squares on the bottom side and 3 squares on the right side. So that's why we say that this is the 2x2 and the 3x3 Aztec diamond. Strangely, if we ask the same question we've been asking throughout this talk of how many minimal inscribed polyominoes are there, no matter what the size is, there are only ever 4. And I know that's very strange because in the past we've seen those sequences growing as the grids get bigger. But whether we have a 2x2 Aztec diamond, a 3x3 Aztec diamond, or an 1000 by 1000 Aztec diamond, the number of minimal inscribed polyforms is always just 4. And it's actually these 4 polyominoes we see, or analogous polyominoes we see in this slide right here. So this is kind of boring. It's only ever 4. And what I decided to do for this question was to break the rules. So I realized I established previously that a polyomino is only considered a polyomino because they're connected edgewise. What I decided was, okay, what if I consider instead a shape that is connected both edgewise and cornerwise? So breaking the cardinal rule of polyominoes, if you will. Now, what we'll do is we'll call these pseudo-polyforms. So they're not quite following the rules, so we'll call them pseudo-polyforms. Here I've provided some examples of pseudo-polyforms in the 3x3 Aztec diamond. So we can kind of get a little bit more familiar with what these specific objects look like. And just like before, we can start talking about the number of pseudo-polyforms for a specific size. We can compute that the number of minimal inscribed pseudo-polyforms for the n by n Aztec diamond, starting at n is 1, begins 1, 68, 1,113, 11,606, and so on. The actual enumeration of this sequence for general n by m Aztec diamonds was an incredibly difficult task and easily amounts to the most difficult math question I've ever solved on my own. So I'm very happy to show this next slide, which is the result. Now, if we let a row of A, S star, and M represent the number of minimal inscribed pseudo-polyforms in the n by m Aztec diamond, then we have the following results. Here we give a generating function, and the reason for that is the exact formula is horribly messy. I mean, this generating function is pretty messy on its own, but it's certainly better than the exact formula. Finally, here are my sources, and I'd like to thank you all very much for watching. Have a good day.